Right now, as you watch this video, the Sun is attacking Earth with the force of 5 billion nuclear bombs. Every single second, our star hurls 1.5 million tons of superheated plasma toward our planet at speeds exceeding 1 million miles per hour. This invisible hurricane of charged particles should have stripped away our atmosphere billions of years ago, leaving Earth as dead and barren as Mars. But something extraordinary is protecting us. An invisible force field generated by the molten iron, churning 1/800 miles beneath your feet. And here's what makes this truly unsettling. Scientists have recently discovered that this protective shield is weakening at an accelerating rate. In some regions, it's already lost 10% of its strength in just the last 2 centuries. What happens when it fails completely? We actually know the answer, because it's happened before, and the evidence is locked in ancient rocks, revealing a catastrophic event that nearly ended life on Earth. If these mind-bending revelations about the invisible war between our planet and the Sun have captured your imagination the way they've captured mine, make sure to hit that like button and subscribe so you don't miss any updates as this story unfolds in real time. Drop a comment telling me where you're watching from, what time it is there, and whether you think Earth's magnetic field will still be protecting us 1,000 years from now. And if you want to help spread awareness about these profound discoveries that could define humanity's future, share this video on X, Facebook, Reddit, or your group chats. You're the reason we can keep investigating these world-changing truths, so thank you for having our back. Now, let's dive into the most important invisible force you've probably never thought about. Section 1. The Silent Guardian. You can't see it, you can't feel it, but right now, an invisible force field is the only thing standing between you and a radiation bath that would make a nuclear disaster look like a sunburn. The Sun isn't just the bright, friendly circle we see in the sky. It's a raging thermonuclear furnace, converting 600 million tons of hydrogen into helium every single second through nuclear fusion. And all that violence doesn't stay contained. The Sun is literally blowing itself into space in what scientists call the solar wind, a supersonic stream of charged particles that rushes outward in all directions at approximately 1 million miles per hour. Let me put that into perspective. Every second, not every minute, not every hour, but every single second, the Sun ejects 1.5 million tons of material. That's roughly the weight of 100,000 full-grown elephants being hurled into space faster than any human-made object has ever travelled. This isn't a gentle breeze. This is a cosmic hurricane of protons, electrons and alpha particles carrying temperatures of 1,000,000 degrees Celsius. When this plasma wall slams into Earth, travelling at speeds between 250 to 750 miles per second, it doesn't just bounce off harmlessly. The solar wind carries enormous energy and electromagnetic force. If Earth were defenceless, this relentless bombardment would gradually strip away our atmosphere, molecule by molecule, until our planet became a barren rock like Mars. But we're not defenceless. Surrounding our planet is an invisible shield called the Magnetosphere, a massive magnetic bubble extending up to 370,000 miles into space on the day side and millions of miles on the night side, stretching beyond the Moon's orbit. This isn't science fiction. This is a scientifically documented force field generated by the rotation of liquid iron and nickel in Earth's outer core, some 1,800 miles beneath your feet. The numbers are staggering. Earth's magnetic field deflects approximately 99.9% of the solar wind's charged particles, channeling them around our planet like water flowing around a rock in a stream. Without this protection, NASA estimates that Earth would lose its atmosphere at a rate similar to what happened to Mars, which lost most of its atmosphere billions of years ago when its magnetic field collapsed. But here's what scientists are now warning us about, and what makes this story deeply unsettling. Earth's magnetic field isn't stable, it's not a permanent feature, and right now, in our lifetime, something extraordinary and potentially catastrophic is happening to it. The field is weakening. Since scientists began measuring it accurately in the 1830s, Earth's magnetic field has weakened by approximately 10% globally, but that's just the average. In a vast region stretching from South America to Southern Africa, an area called the South Atlantic Anomaly, the field has weakened by more than 30% in some locations. Satellites passing through this weakened zone experience higher rates of computer malfunctions and electronic failures due to increased radiation exposure. The Hubble Space Telescope is routinely shut down when it passes through this region to prevent damage to its sensitive instruments. Commercial airlines now avoid certain flight paths over the South Atlantic because of elevated radiation risks to passengers and crew. What's causing this weakening? Why is it happening now? And most importantly, what happens if it continues? To understand the answers, we need to journey to the centre of the Earth and uncover one of the most remarkable and terrifying phenomena in planetary science. Section 2. The Iron Heart. Deep beneath your feet, deeper than any human has ever travelled, lies the true source of Earth's protective shield. And it's far stranger than most people realise. The journey to Earth's core is a descent through increasingly hostile environments. First, you'd pass through the crust, the thin shell of rock we live on, averaging just 18 miles thick. Then comes the mantle, a 800-mile thick layer of semi-solid rock heated to thousands of degrees. But the real marvel lies deeper still. At 1,800 miles down, you'd reach the outer core, a roiling ocean of liquid iron and nickel, heated to temperatures between 4,000 and 5,000 degrees Celsius. This molten metal ocean is roughly the size of Mars, and it's constantly in motion, churning and flowing in complex patterns driven by Earth's rotation and heat, escaping from the even deeper inner core. And here's where it gets fascinating. This flowing liquid metal is electrically conductive. As it moves, it generates electric currents. Those electric currents in turn generate magnetic fields, and those magnetic fields influence the motion of the conductive fluid, which generates more current, which creates more magnetic fields, in a self-sustaining loop called a geodynamo. This is the engine that powers Earth's magnetosphere, a natural dynamo 1,800 miles beneath the surface, running continuously for over 3.5 billion years. The process is called the geodynamo effect, and while scientists understand the basic principle, the exact mechanisms remain one of Earth science's great mysteries. The flow patterns in the outer core are phenomenally complex, involving turbulence, convection, and the effects of Earth's rotation. Supercomputers at institutions like NASA's Jet Propulsion Laboratory and the European Space Agency run for months to simulate just a few decades of core dynamics. Dr. Peter Olsen, a geophysicist at Johns Hopkins University, describes the outer core as the most inaccessible and least understood region of our planet. We've sent probes to every planet in our solar system and beyond, but we've never directly sampled material from Earth's outer core. Everything we know comes from indirect measurements, seismic waves from earthquakes, measurements of Earth's magnetic field from satellites and ground stations, and sophisticated computer simulations. But here's what those measurements have revealed. Something that should make every person on this planet pay attention. The geodynamo isn't steady. The magnetic field it generates fluctuates constantly. The magnetic poles wander across Earth's surface year by year. The field's strength varies regionally and over time, and occasionally something truly extraordinary happens, something that would seem impossible if we didn't have rock-solid geological evidence proving it's real. The magnetic field completely reverses. North becomes south. South becomes north. The magnetic poles flip. This isn't speculation or theory. It's a geological fact recorded in iron-rich rocks formed millions of years ago. When volcanic rocks cool and solidify, magnetic minerals within them align with Earth's magnetic field at that moment, creating a permanent record of the field's direction, a process called thermoremanent magnetization. By studying rocks of different ages from around the world, Geologists have reconstructed Earth's magnetic history going back hundreds of millions of years, and what they've discovered is deeply unsettling. Magnetic reversals happen regularly throughout Earth's history. The last one occurred approximately 780,000 years ago, an event known as the Brunhes-Matuyama reversal. Before that, reversals occurred roughly every 200,000 to 300,000 years on average, though the intervals vary wildly. Some reversals are separated by millions of years, others by just tens of thousands. But here's what makes our current situation particularly alarming. We're overdue. It's been 780,000 years since the last reversal, nearly 4 times longer than the average interval. And the current weakening of Earth's magnetic field, combined with the rapid movement of the magnetic North Pole and the expansion of the South Atlantic anomaly, has led many scientists to a disturbing conclusion. We might be in the early stages of a magnetic reversal right now. Dr. Daniel Baker, director of the Laboratory for Atmospheric and Space Physics at the University of Colorado, has stated that the signs are suggestive of a possible reversal event. European Space Agency data from their Swarm satellite constellation, launched specifically to study Earth's magnetic field, shows accelerating changes that fit models of reversal initiation. But here's the question that should terrify you. What happens to life on Earth when the magnetic field reverses? What happens during the transition period, when the field potentially weakens to a fraction of its current strength? To answer that, we need to look at what happened 42,000 years ago, during an event that scientists only recently discovered. An event that may have brought human civilization to the brink of extinction. Section 3. The Lachamps Event. In 2021, a team of international scientists published a study in the journal Science that sent shockwaves through the scientific community. They had uncovered evidence of a catastrophic event 42,000 years ago, an event that coincided with the extinction of megafauna, the disappearance of Neanderthals, and dramatic changes in human behaviour reflected in cave art and archaeological records. They called it the Adams Event, named after Douglas Adams' Hitchhiker's Guide to the Galaxy, where 42 is the answer to life, the universe, and everything. But this wasn't science fiction. This was a scientific fact, and it revealed something terrifying about what happens when Earth's magnetic shield fails. The discovery centred around ancient kauri trees found preserved in New Zealand's swamps. These trees lived during a period called the Lachamps Excursion, a geomagnetic event approximately 42,000 years ago, when Earth's magnetic field strength dropped to just 6% of today's levels. The magnetic poles wandered dramatically, and for a period of several centuries the field was so weak it provided almost no protection against cosmic radiation and solar wind. By analysing the radiocarbon content in the tree rings of these ancient kauri trees, scientists could reconstruct atmospheric conditions year by year during this period. What they found was shocking. During the weakest point of the Lachamps excursion, cosmic radiation reaching Earth's surface increased by 200–300%. The atmosphere experienced dramatic chemical changes. The ozone layer, which protects us from ultraviolet radiation, was severely depleted. Electrical storms became more frequent and intense. The Aurora Borealis and Aurora Australis, normally confined to polar regions, extended down to the equator, filling the skies over Europe, Africa and Asia with dancing lights never seen before. Imagine standing 42,000 years ago in what is now France or Spain. The northern horizon glows with shifting curtains of green, red and purple light, an aurora that shouldn't be visible this far south. Electrical storms crackle with unprecedented intensity. The sun, stripped of the magnetic filtering effect, bathes the landscape in higher levels of ultraviolet radiation. Cosmic rays stream through the weakened magnetic field, ionizing the atmosphere and potentially affecting DNA mutation rates in all living organisms. Dr. Alan Cooper, one of the study's lead authors from the South Australian Museum, stated, It would have been an incredibly scary time, kind of like the end of days, and the timing is deeply suspicious. The Lashom excursion coincides with a period of dramatic change in the archaeological record. Neanderthals, who had survived for over 300,000 years, disappeared from Europe. Cave art became dramatically more sophisticated, with humans suddenly creating elaborate paintings deep in caves, possibly seeking shelter from increased radiation or from the terrifying auroras filling the sky. Red ochre, which provides some protection from ultraviolet radiation, became widely used in body painting and cave art. Large mammals went extinct. Climate patterns shifted dramatically. The archaeological record shows evidence of widespread environmental stress. Could all of this be related to the magnetic field collapse? The timing suggests yes, but the mechanisms are complex and still debated. Higher cosmic radiation could have increased DNA mutation rates, putting evolutionary pressure on all species. Increased cloud formation, triggered by cosmic ray seeding of water vapor nucleation, could have altered climate patterns. Ozone depletion would have increased surface UV radiation, harming ecosystems. The psychological impact of dramatic sky phenomena and increased solar activity might have influenced human behavior and migration patterns. But here's what's really disturbing. The Lashon's excursion wasn't a full magnetic reversal. It was just a temporary weakening and wobble of the field, what scientists call an excursion. The field recovered after several centuries without fully reversing polarity. A true reversal, like the Brunhes-Matuyama event 780,000 years ago, would be far more severe and could last much longer. Geological evidence suggests that reversals can take anywhere from 1,000 to 10,000 years to complete, during which time the magnetic field structure becomes chaotic, with multiple magnetic poles appearing and disappearing, and the field strength potentially dropping to just 10–20% of normal levels for thousands of years. What would that mean for modern civilization? We're not hunter-gatherers living in small tribal groups anymore. We're a technological species of 8 billion people, dependent on satellites, power grids, GPS systems, and electronic infrastructure, all of which are vulnerable to the very thing Earth's magnetic field protects us from. Which brings us to the next terrifying question. What happens when the solar wind isn't just a constant breeze, but a Category 5 hurricane? What happens during a solar storm? Because while the sun is always attacking us, sometimes it attacks with the force of 1 billion nuclear bombs, and it's happened in living memory. Section 4. The Carrington Event, September 1st, 1859. British astronomer Richard Carrington was doing what he did every clear day, observing and sketching sunspots through his telescope at his private observatory. But on this particular morning, something extraordinary happened. Carrington watched in amazement as 2 brilliant white flashes erupted from a massive sunspot group. The flashes lasted only about 5 minutes, but Carrington knew he'd witnessed something unprecedented. A solar flare, the first ever observed by human eyes. What Carrington didn't know was that he'd just seen the warning shot of the most powerful solar storm in recorded history, an event that would, 17 hours later, cause technological chaos across the entire planet. At 1 a.m. on September 2nd, 1859, the night sky exploded with colour. Auroras appeared as far south as Cuba, Hawaii and Colombia, places where auroras had never been seen before or since. The lights were so bright that people in the northeastern United States could read newspapers by their glow. Miners in the Rocky Mountains woke up at 2 a.m. thinking it was dawn and began preparing breakfast. But the auroras were just the visible symptom of something far more dramatic happening in Earth's magnetosphere. The solar storm, now called the Carrington Event, slammed into Earth's magnetic field with unprecedented force, compressing it dramatically and allowing charged particles to cascade down into the upper atmosphere. And then the real chaos began. Telegraph systems worldwide went haywire. Telegraph operators received electrical shocks from their equipment. The telegraph paper spontaneously caught fire. Most remarkably, even when operators disconnected the batteries powering their telegraph systems, the lines continued working, powered entirely by the electrical currents induced by the fluctuating magnetic fields from the solar storm. In 1859, humanity's technological infrastructure consisted primarily of telegraph lines. Today, we have power grids, satellites, GPS systems, internet infrastructure, and countless electronic devices. What would a Carrington-level event do to our modern civilization? We came dangerously close to finding out in 2012. On July 23, 2012, the Sun unleashed a solar storm of Carrington-class intensity. A massive coronal mass ejection, CME, carrying billions of tons of plasma at speeds exceeding 2,000 miles per second. If it had erupted 1 week earlier, it would have hit Earth directly. Dr. Daniel Baker of the University of Colorado, who led a study on the event, stated, "If it had hit, we would still be picking up the pieces." NASA estimated the economic impact of such an event at over $2 trillion, 20 times the cost of Hurricane Katrina, with recovery taking 4 to 10 years. But we got lucky. The CME missed Earth by just 9 days of planetary rotation. Instead of hitting our planet, it tore through Earth's orbital path, hitting the Stereo A spacecraft, which survived to send back data on the storm's intensity. Analysis of that data was sobering. The 2012 event was comparable to, or possibly stronger than, the Carrington event. If it had hit Earth, here's what likely would have happened. Within seconds of impact, the planet's magnetosphere would have been violently compressed. Massive electrical currents would have been induced in anything conductive on Earth's surface. Power lines, transformers, undersea cables, pipelines. Power grids would begin failing within minutes. High-voltage transformers, the critical components that step electricity down from transmission voltages to usable levels, would overheat and fail. Unlike simple power failures that can be fixed quickly, transformer damage from solar storm-induced currents requires replacement of massive custom-built equipment that takes months or years to manufacture. Within the first hour, much of the Northern Hemisphere's power grid could be down. Satellites would begin failing as their electronics were fried by the intense radiation. GPS systems would become unreliable or completely non-functional. Radio communications would be disrupted. Airlines would lose crucial navigation and communication systems. Within 24 hours, the cascading failures would become catastrophic. With no power, water pumping stations would fail. Sewage systems would back up. Gas stations couldn't pump fuel. Hospitals would run on emergency generators until fuel ran out. Food refrigeration would fail. The just-in-time supply chains that modern cities depend on would collapse. Within a week, major cities would become uninhabitable. Without power for water purification and pumping, millions would lack clean drinking water. Without refrigeration and functioning supply chains, food would become scarce. Civil unrest would be inevitable. Studies by the National Academy of Sciences and the Department of Homeland Security paint a grim picture of what a Carrington-level event would mean for modern civilization. Widespread power grid failure, affecting hundreds of millions of people. Disruption of satellite systems affecting communications and GPS navigation globally. Potential transformer damage requiring years to fully repair. Economic losses in the trillions of dollars, and potential societal breakdown in affected regions. But here's the truly terrifying part. The Carrington event wasn't even the worst solar storm in Earth's recent history. Ice core data has revealed evidence of even more powerful solar events. In 775 CE, Earth was hit by what scientists call a Miyake event, a solar storm so powerful that it left a distinctive carbon-14 spike in tree rings and ice cores worldwide. Analysis suggests this event was 10 to 50 times more powerful than the Carrington event. Another Miyake event occurred around 993 CE. Both events predated modern technology, so we don't know what the consequences were for medieval societies. But if a similar event hit today, the consequences would be almost unimaginable. And here's the critical connection. All of these calculations, all of these scenarios, assume Earth's magnetic field is at full strength. They assume our shield is operating normally, deflecting 99.9% of the solar wind and absorbing much of the solar storm's impact. But what if it's not? What if we're hit by a major solar storm during a period of magnetic field weakening, like the period we're in right now? What if a Carrington-level event hit Earth while we were experiencing a Lachamp-style excursion, or worse, during an actual magnetic reversal? The answer is chilling. Nobody really knows because it's never happened during recorded human history. But scientists are desperately trying to find out, and what they're discovering is keeping them awake at night. Section 5. The South Atlantic Anomaly. There's a region above Earth where satellites go to die, or at least where they experience mysterious malfunctions, computer reboots, and instrument failures at rates far higher than anywhere else. It's called the South Atlantic Anomaly, and it's growing. The South Atlantic Anomaly is a vast region stretching from South America across the Atlantic Ocean to southern Africa, where Earth's magnetic field strength is significantly weaker than the global average, up to 30% weaker in some locations. In this region, the protective magnetic shield is thinner, allowing higher levels of radiation to penetrate closer to Earth's surface. For satellites orbiting at low Earth orbit altitudes, between 200 and 1,000 miles up, passing through the South Atlantic Anomaly means passing through a region of increased radiation exposure. The effects are measurable and concerning. The Hubble Space Telescope cannot make observations when passing through the anomaly. Its sensitive instruments are shut down to prevent damage and corrupted data. The International Space Station's crew is instructed to avoid certain activities and stay in more heavily shielded modules when passing through the region. Astronauts receive elevated radiation doses, measurably higher than during other parts of their orbit. Earth observation satellites frequently experience pixel distortions and data corruption when imaging areas within the anomaly. Communication satellites experience increased bit flip errors, random changes to data caused by radiation striking computer memory chips. Some satellites have been lost entirely due to failures coinciding with passes through the region. The phenomenon isn't new, it's been known since the early days of space exploration. But what's alarming scientists now is that the anomaly is growing and changing in ways that suggest something fundamental is happening deep within Earth's core. Data from the European Space Agency's Swarm satellite constellation, launched in 2013 specifically to study Earth's magnetic field in unprecedented detail, has revealed disturbing trends. The South Atlantic Anomaly is not only persisting, but it's expanding westward and weakening further. Between 1970 and 2020, the anomaly has grown by approximately 8% and weakened by an additional 8% in strength. But that's not all. In 2020, satellite observations revealed something unexpected. The anomaly is splitting into two distinct centres of weakness, one over South America and another over the South Atlantic Ocean near Africa. This bifurcation wasn't predicted by models and suggests that the dynamics in Earth's outer core are more complex and changing more rapidly than previously understood. Dr. Jürgen Matzke from the German Research Center for Geosciences explained, "The new eastern minimum of the South Atlantic Anomaly has appeared over the last decade and in recent years is developing vigorously. We are very lucky to have the Swarm, satellites in orbit to investigate the development of the South Atlantic Anomaly. But lucky might not be the right word. The data Swarm is collecting is deeply concerning. Computer models of Earth's geodynamo show that the South Atlantic Anomaly is linked to peculiar structures deep in the Earth's core. Specifically, there appears to be a region of reversed magnetic flux beneath southern Africa, an area where the magnetic field lines are pointing in the opposite direction from what they should. This reversed flux patch is influencing the flow of liquid iron in the outer core, creating the weakened field strength we observe at the surface. And according to some models, this reversed flux patch is growing and could be the first sign of an impending magnetic reversal. Dr. Phil Livermore, a geophysicist at the University of Leeds, has been studying these deep core structures using sophisticated computer models. His team's research suggests that the reversed flux patch beneath Africa is part of a larger pattern of magnetic field instability that has been developing for thousands of years. What we're seeing, Dr. Livermore explained in a 2020 interview, is potentially the early stages of a magnetic field reversal. But these processes take thousands of years to play out, so we're really witnessing just a snapshot of a much longer process. But here's where it gets even more unsettling. The rate of change appears to be accelerating. Measurements of magnetic field strength from observatories around the world show that the global average field strength has declined by about 5% per century since accurate measurements began in the 1840s. But in recent decades, that rate has increased. In the South Atlantic anomaly region, the decline is even more dramatic, about 10% per decade in some locations. The magnetic North Pole, the point where Earth's magnetic field points straight down, has also been behaving strangely. For most of recorded history, the magnetic North Pole was located in northern Canada, moving at a sedate pace of about 9 miles per year. But since the 1990s, the pole has accelerated dramatically, racing towards Siberia at speeds exceeding 35 miles per year. In 2019, the pole's movement was so rapid that the World Magnetic Model, the mathematical model used for navigation systems from smartphone compasses to military applications, had to be updated a year ahead of schedule. The model is normally updated every 5 years, but the pole's unexpected acceleration made the old model unacceptably inaccurate. Dr. Ciaran Began, a geophysicist at the British Geological Survey, described the situation. The magnetic pole has been moving so quickly that the error in navigation systems was approaching unacceptable levels. We had to issue an emergency update. All of these phenomena, the South Atlantic anomaly's growth and weakening, its splitting into two centres, the accelerating movement of the magnetic North Pole, and the overall decline in global field strength, paint a picture of a magnetic field in flux, potentially in the early stages of a reversal event. But what's actually happening deep in the core? Why is this happening now? And most importantly, is there anything we can do about it? To answer those questions, we need to understand the most recent scientific insights into Earth's deep interior. Insights that come from an unlikely source. The most powerful supercomputers on Earth running simulations that take months to complete, and from satellites orbiting hundreds of miles above our heads, listening to the magnetic whispers rising from 1-800 miles below. Section 6. Secrets of the Iron Ocean. Deep beneath Africa, something strange is happening. At the boundary between Earth's molten outer core and the solid mantle above it, a depth of 1,800 miles, there are two massive structures unlike anything else in our planet's interior. They're called Large Low Shear Velocity Provinces, or LLSVPs, but scientists informally call them the blobs. These structures are continent-sized regions where seismic waves travel more slowly, suggesting they're hotter or chemically different from the surrounding mantle. One blob sits beneath Africa, the other beneath the Pacific Ocean. And here's where it gets fascinating. These blobs appear to be influencing the flow of liquid iron in the outer core beneath them, which in turn affects Earth's magnetic field at the surface thousands of miles above. The African blob, in particular, sits directly beneath the region where the South Atlantic anomaly appears at the surface. This can't be a coincidence. Dr. Julien Aubert, a computational geophysicist at the Paris Institute of Earth Physics, has developed some of the most sophisticated computer models of Earth's core dynamics. His simulations, running on supercomputers for months at a time, have revealed how structures at the core mantle boundary influence the geodynamo. The mantle isn't uniform, Dr. Aubert explained in a 2020 research paper. It has temperature variations, chemical variations, and these large-scale structures that affect heat flow from the core. Where heat escapes more efficiently from the core, the convection patterns in the liquid iron change, and that changes the magnetic field. The African blob appears to be disrupting normal convection patterns in the outer core beneath it. The altered flow patterns are creating regions of reversed magnetic flux, places where magnetic field lines point in the opposite direction from the main field. These reversed flux patches are what ultimately create weak spots in the magnetic field at Earth's surface, like the South Atlantic anomaly. But these aren't small temporary features. The African blob has been sitting in roughly the same location for tens of millions of years. The reversed flux patches have been present for thousands of years and appear to be growing. Computer simulations show that when reversed flux patches grow large enough, they can trigger a magnetic reversal. The process works like this. As reversed flux patches grow, they begin to dominate larger regions of the core. Normal flux and reversed flux interact in complex ways, creating turbulence and instability. Eventually, the reversed flux can become strong enough to overpower the normal field. When that happens, the entire field structure can flip. North becomes south, south becomes north. The process isn't instantaneous. Simulations suggest it takes 1,000 to 10,000 years to complete a reversal. During the transition period, the field structure becomes chaotic. Multiple north and south poles appear and disappear. The overall field strength drops dramatically, potentially to just 10-20% of normal levels, and throughout this period, Earth's protection from solar wind and cosmic radiation is severely compromised. But here's what's keeping scientists awake at night. We don't fully understand what triggers the transition from a stable, reversed flux patch to a full-blown reversal. The dynamics are enormously complex, involving turbulent flow of liquid metal on enormous scales, the effects of Earth's rotation, heat flow from the inner core, and interactions with the overlying mantle. Dr. Gary Glatzmeyer, a computational astrophysicist at the University of California, Santa Cruz, was part of the team that created the first computer simulation to successfully reproduce a magnetic reversal in 1995. Even with decades of subsequent improvements, the model still can't predict when the next reversal will occur. The core is one of the last frontiers of Earth science, Dr. Glatzmeyer said in a 2019 interview. We can't go there, we can't sample it, we can only infer what's happening from surface measurements and computer models. And the models are only as good as our understanding of the physics involved. What the models do show, consistently, is that magnetic reversals are a normal part of Earth's magnetic field behaviour. Over the past 20 million years, reversals have occurred on average every 200,000 to 300,000 years. But the intervals are irregular. Sometimes 1 million years pass between reversals, other times just tens of thousands of years. The geological record preserved in seafloor volcanic rocks reveals a striking pattern. New ocean crust forms at mid-ocean ridges where tectonic plates spread apart. As the molten rock solidifies, magnetic minerals align with Earth's field, creating alternating stripes of normal and reversed magnetic polarity as the field reverses over millions of years. By mapping these magnetic stripes, geologists have reconstructed Earth's reversal history going back over 160 million years. The pattern is clear. Reversals happen. They're inevitable, and we're overdue. The Brunhes-Matuyama reversal, which occurred 780,000 years ago, was the last full reversal. Before that, the Matuyama-Gauss reversal occurred about 2.5 million years ago. The gap between those reversals was exceptionally long, about 1.78 million years. Since then, reversals have been more frequent, happening roughly every 200,000 to 400,000 years, until now. We're currently in the longest stable period since the Matuyama epoch, 780,000 years and counting. Statistical analysis suggests we're not just overdue, we're very overdue. If reversals were random events occurring with a fixed probability per year, the chances of going 780,000 years without a reversal, given the historical average interval, would be less than 5%. But reversals aren't random. They're driven by complex physical processes in the core, and those processes appear to be reaching a critical point. The question isn't if the next reversal will happen. The question is when, and whether we'll be ready. Because here's the uncomfortable truth. When the magnetic field weakens during a reversal, all of those threats we've discussed, solar storms, cosmic radiation, atmospheric stripping, become dramatically more dangerous. And we're not just talking about threats to our technology, we're talking about threats to life itself. Which brings us to one of the most controversial and frightening questions in modern science. Could a magnetic reversal cause a mass extinction? Section 7. The Extinction Connection. The fossil record tells a story written in stone, a chronicle of life on Earth spanning billions of years. And within that record are distinct boundaries, moments in time when large percentages of species suddenly disappear. We call them mass extinctions. The most famous is the end Cretaceous extinction 66 million years ago, when an asteroid impact killed the dinosaurs and 3/4 of all species on Earth. But there have been 5 major mass extinctions in Earth's history and dozens of smaller extinction events. And here's the disturbing question that a small group of scientists has been asking. Could some of these extinctions be linked to magnetic reversals? The idea is controversial. Most paleontologists attribute extinctions to clearly identifiable causes: asteroid impacts, massive volcanic eruptions, climate change, and ocean acidification. The idea that a magnetic reversal could cause an extinction seems far-fetched at first glance, but the timing is suspicious. In 2012, a team of researchers led by Dr. Robert Simcoe at MIT published a study analysing the timing of extinction events over the past 500 million years. They found a weak but statistically significant correlation between periods of frequent magnetic reversals and elevated extinction rates. The mechanism isn't direct. A magnetic reversal wouldn't kill organisms outright, but it could create conditions that make survival much harder. During a magnetic reversal, when the field strength drops to 10–20% of normal, several things happen. First, cosmic radiation reaching Earth's surface increases dramatically. Studies of the La Chance excursion showed a 200–300% increase in cosmic ray flux. During a full reversal, lasting thousands of years, the increase could be even more severe. Cosmic rays are high-energy particles, primarily protons, travelling at nearly the speed of light. When they strike Earth's atmosphere, they create cascades of secondary particles. A cosmic ray shower that extends down to sea level. Higher cosmic ray flux means more radiation exposure for all life on Earth's surface. The effects could be subtle but cumulative. Increased mutation rates in DNA could put evolutionary pressure on species. Organisms with longer generation times and slower reproductive rates, like large mammals, would be particularly vulnerable. Cancer rates could increase. Reproductive success could decrease. Second, the ozone layer could be depleted. Cosmic rays create nitrogen oxides in the atmosphere through a complex chain of chemical reactions. Nitrogen oxides destroy ozone. With weakened magnetic protection, the continuous bombardment of cosmic rays could progressively thin the ozone layer, allowing more ultraviolet radiation from the sun to reach the surface. UV radiation is directly harmful to DNA, particularly in organisms without protective coloration or behaviours. Marine plankton, which form the base of ocean food chains, are particularly vulnerable to UV damage. A decline in plankton populations could cascade through entire marine ecosystems. Third, the climate could be affected. Cosmic rays play a role in cloud formation. They provide ionization sites where water vapor can condense. Increased cosmic radiation could lead to increased cloud cover, potentially cooling the planet. This hypothesis, called cosmoclimatology, is controversial and not fully accepted by mainstream climate science, but there is some evidence supporting a cosmic ray cloud connection. If magnetic reversals do influence climate through cosmic ray-mediated cloud formation, then periods of frequent reversals could lead to climate instability. Rapid shifts between warmer and cooler periods that put stress on ecosystems and contribute to extinctions. But here's where the evidence becomes really interesting and disturbing. Around 42,000 years ago, during the La Chance excursion, we see evidence of all these effects. The tree ring data shows increased cosmic radiation. Cave art and archaeological evidence suggest behavioural changes in humans. Megafauna extinctions cluster around this time. Climate records show instability. And the La Chance excursion wasn't even a full reversal. It was just a temporary weakening and wobble of the field that lasted a few centuries. What about actual reversals, which last thousands of years? Dr. James Channell, a paleoceanographer at the University of Florida, has spent decades studying the relationship between magnetic reversals and climate recorded in ocean sediment cores. His research has found evidence of climate disruptions coinciding with several reversal events over the past few million years. The correlations aren't perfect, Dr. Channell admitted in a 2018 paper, but there are enough coincidences to warrant serious investigation. We can't dismiss the possibility that magnetic field behaviour has influenced Earth's climate and biosphere in ways we don't fully understand yet. Perhaps the most compelling evidence comes from detailed studies of the Brunnes-Matuyama reversal 780,000 years ago. This reversal occurred during a critical time in human evolution. Homo erectus populations were widespread across Africa, Asia, and Europe. What happened to them during the reversal? Fossil evidence from this period is sparse, but there are hints of population bottlenecks, periods when human populations dramatically declined. Genetic studies of modern human DNA suggest that around 800,000 years ago, human ancestors went through a severe population bottleneck, reducing to perhaps just 18,500 individuals capable of breeding. Could this bottleneck be related to the Brunhes-Matuyama reversal? The timing is suggestive, but proving causation is difficult. What we do know is this. During the Brunhes-Matuyama reversal, which took about 7,000 years to complete, there were periods when Earth had 4 or more magnetic poles simultaneously. The magnetic field strength dropped to very low levels, and this occurred during a period of significant climate change and evolutionary pressure. But here's the critical difference between then and now. The human population 780,000 years ago was small, scattered, and adapted to living in small groups with Stone Age technology. They could migrate to avoid hazards. They could shelter in caves. They had no power grids, no satellites, no technology that could fail. We do. Modern civilization is built on a technological infrastructure that assumes a stable, protective magnetic field. Our satellites, our power grids, our communication systems, all evolved in an environment of relatively strong, stable magnetic protection. We've never had to face the challenge of maintaining a technological civilization through a magnetic reversal, and the uncomfortable truth is that nobody knows if it's even possible. Which brings us to the question that should concern everyone on this planet. What is our civilization doing to prepare for the next reversal? Are governments and space agencies taking this threat seriously? And is there anything we can actually do to protect ourselves? The answers are complex, often classified, and in some cases deeply disturbing. Section 8, the government response. In January 2019, the US National Science and Technology Council published a document that received surprisingly little media attention considering its implications. It was called National SpaceWeather Strategy and Action Plan, and buried within its pages was a stark acknowledgement of what government agencies have been quietly preparing for. The document outlined scenarios for what would happen if a major solar storm struck Earth during a period of weakened magnetic protection. The conclusions were sobering. Widespread power grid failures affecting up to 130 million people in the United States alone, satellite failures disrupting GPS and communications globally, economic losses exceeding $2 trillion, and recovery times potentially lasting 4 to 10 years. But here's what's interesting. The document doesn't just focus on solar storms. It explicitly mentions the South Atlantic anomaly's expansion and the potential for magnetic field weakening to compound the effects of space weather events. This wasn't fear-mongering. This was the US government officially acknowledging that Earth's magnetic shield is changing, that the changes could accelerate and that we need to prepare. So what are they doing about it? The answer involves satellites, supercomputers, power grid hardening, and contingency plans that most citizens know nothing about. First, the satellites. The European Space Agency's Swarm constellation, launched in 2013, is specifically designed to monitor Earth's magnetic field from orbit. 3 identical satellites fly in different orbits, continuously measuring magnetic field strength, direction, and variations with unprecedented accuracy. The data from Swarm has been revolutionary. Before Swarm, our understanding of the magnetic field was limited by sparse ground-based measurements and older, less sophisticated satellites. Swarm provides global, continuous coverage, revealing details of the field structure and changes that were invisible before. NASA has its own magnetic field monitoring satellites, including the Magnetospheric Multiscale (MMS) mission, which studies how the magnetic field interacts with the solar wind. The data from MMS has revealed that the interaction is far more complex and dynamic than previously thought, with magnetic reconnection events allowing solar wind particles to penetrate the magnetosphere in ways that weren't predicted by earlier models. But satellites just collect data. Understanding what the data means requires supercomputers running sophisticated simulations of core dynamics. the US Department of Energy operates some of the world's most powerful supercomputers at facilities like Oak Ridge National Laboratory and Lawrence Livermore National Laboratory. These machines aren't just used for nuclear weapon simulations, they're also running geodynamo models, attempting to understand and predict how Earth's magnetic field will evolve over the coming decades and centuries. Dr. Peter Driscoll at the Carnegie Institution for Science runs geodynamo simulations that can take months of supercomputer time to complete. His models have revealed that the magnetic field's evolution is extremely sensitive to conditions in the deep core. Small changes in heat flow or composition can lead to dramatically different outcomes over time. The core is a chaotic system, Dr. Driscoll explained in a 2020 interview. Small perturbations can cascade into major changes. That makes long-term prediction extremely difficult. We can identify trends and possibilities, but we can't say with certainty that a reversal will begin in 100 years versus 10,000 years. That uncertainty makes planning difficult. But some preparations are underway, particularly for the more immediate threat of solar storms. Power companies in the United States, Europe, and other developed countries have been quietly hardening their infrastructure against geomagnetic storms. The most vulnerable components are large transformers, which can be damaged by geomagnetically induced currents flowing through power lines during solar storms. After the March 1989 geomagnetic storm knocked out power to 6 million people in Quebec, Canada, for 9 hours, power companies began taking the threat more seriously. Modern grid designs incorporate monitoring systems that can detect early signs of geomagnetically induced currents and automatically shut down vulnerable transformers before damage occurs. But this protection is far from comprehensive. A 2019 report by the US Government Accountability Office found that while some utilities have implemented protective measures, many have not, leaving large portions of the grid vulnerable to a major geomagnetic storm. The situation is even worse in developing countries. Much of Africa, South America, and Asia has minimal to no geomagnetic storm protection. If a major event occurred, the damage could be catastrophic, and recovery could take years or even decades in some regions. Satellite operators have also adapted. Modern satellites are built with radiation-hardened electronics and redundant systems specifically designed to survive the increased radiation exposure during solar storms. Satellites can be put into safe mode during major space weather events, shutting down non-essential systems to prevent damage. But there's a limit to how much protection can be built in. Satellites passing through the South Atlantic anomaly still experience elevated failure rates, and if the anomaly continues to expand and weaken, satellite operations could become increasingly difficult, or even impossible in certain orbital configurations. Perhaps most concerning are the contingency plans that governments have developed but rarely discuss publicly. In 2012, the leaked documents from the UK government revealed plans for dealing with a catastrophic solar storm, including provisions for declaring martial law, rationing food and fuel, and managing mass evacuations from major cities if power could not be restored. Similar contingency plans exist in the United States, though most remain classified. What is public knowledge is that FEMA, Federal Emergency Management Agency, has designated solar storms and geomagnetic disturbances as potential catastrophic national disasters on par with major earthquakes, pandemics, and nuclear events. But here's the critical limitation. All of these plans, all of these preparations assume a stable or slowly changing magnetic field. They're designed to handle temporary solar storm events, not a long-term, multi-century or multi-millennia weakening during a magnetic reversal. Nobody has a plan for maintaining technological civilization through a full magnetic reversal, because nobody knows if it's possible. The best we can do is monitor the situation, try to understand what's happening in the core, and prepare for the worst. Which brings us to one of the most fascinating and controversial aspects of this entire story: the role of amateur researchers, independent scientists, and underground networks of observers who are tracking Earth's magnetic field with a dedication and urgency that sometimes exceeds official efforts. Because while governments and space agencies slowly acknowledge the threat, there's a global community of people who have been sounding the alarm for years, collecting data, and making predictions that are both fascinating and terrifying. Section 9. The Amateur Detectives. Not all scientific discovery happens in university labs or government facilities. Sometimes the most important observations come from dedicated amateurs, people with passion, curiosity, and increasingly access to technology that would have been unimaginable a generation ago. Earth's magnetic field has attracted a dedicated community of amateur researchers who monitor field strength, track the magnetic poles, and discuss anomalies with an intensity that borders on obsession, and some of what they've discovered has been truly remarkable. Stuart Green is a retired software engineer living in Scotland. In 2015, he set up a homemade magnetometer in his backyard, a simple device that measures magnetic field strength using sensors that cost less than $100. He began recording data every minute, 24 hours a day, and uploading the results to a website where other amateur researchers could access them. "I just wanted to see what was happening," Stuart explained in a 2019 interview with the Science podcast. "The official observatories publish data, but often with delays. I wanted real-time information." What Stuart and others like him have observed is fascinating. The magnetic field isn't just slowly weakening, it fluctuates constantly, with short-term variations caused by solar-wind interactions and longer-term trends that match the patterns observed by satellites and official observatories. But here's where it gets interesting. The amateur network sometimes detects anomalies before official sources acknowledge them. In 2017, several amateur magnetometer operators noticed unusual fluctuations in field strength over a period of several weeks. The fluctuations didn't correlate with any known solar activity. When they compared notes online, they discovered that observers across Europe and North America were seeing the same patterns. It took several months before academic researchers published an analysis of the event, which turned out to be caused by unusual activity in the core generating what's called a geomagnetic jerk, a sudden change in the rate of magnetic field change. The amateurs had detected it in real time, while the official science community took months to analyse and publish. This type of citizen science has become increasingly sophisticated. Projects like Intermagnet, International Real-Time Magnetic Observatory Network, coordinate data from hundreds of official and amateur magnetic observatories worldwide, creating a global monitoring network with unprecedented coverage. But not all amateur researchers are content with just observing. Some are making bold predictions about when the next reversal will occur, predictions that range from reasonably scientific to wildly speculative. Dr. Ben Davidson, who runs the YouTube channel Suspicious of Bee Servers, has built a following of over 400,000 subscribers by analysing space weather, magnetic field data, and solar activity. His videos blend legitimate science with more speculative interpretations, arguing that Earth is in the early stages of a rapid magnetic excursion or reversal that could occur within decades rather than millennia. The mainstream scientific narrative is that reversals take thousands of years, Davidson argued in a 2020 video. But what if they're wrong? What if the geological record is being misinterpreted and reversals can happen much faster, even catastrophically fast? This is where amateur research becomes controversial. The mainstream scientific consensus based on geological evidence is clear. Magnetic reversals take thousands of years to complete. The transition isn't sudden. There's no evidence in the geological record of a magnetic field flip happening in months or even years. But some amateur researchers argue that the geological record might not capture rapid events effectively. If a reversal happened over just a few decades, would we necessarily see clear evidence in rocks formed millions of years ago? The resolution of the geological record has limits. Dr. Brad Singer, a geochronologist at the University of Wisconsin-Madison, has been working to improve the dating precision of magnetic reversals. Using advanced radiometric dating techniques, his team has been able to constrain the duration of past reversals with greater accuracy than ever before. What we're finding, Dr. Singer explained in a 2019 paper published in Science Advances, is that reversals are complex events with multiple phases. The fastest phase, when the field actually flips polarity, can occur in less than 100 years. But the entire process, from initial weakening to final stabilization, takes several thousand years. This finding is important because it suggests that while the overall reversal process is slow, there could be periods of rapid change within that longer timeline. A 100-year flip would still be catastrophic for modern civilization, even if the complete reversal process takes 5,000 years. The amateur research community has also been tracking the magnetic North Pole's accelerating movement. Using publicly available data from NOAA, National Oceanic and Atmospheric Administration, and the British Geological Survey, amateur analysts created visualizations showing the pole's trajectory from northern Canada towards Siberia. What they found was striking. The pole's movement isn't just accelerating, it's following a curved path that suggests it might be responding to the growing reverse flux patch beneath Siberia. If this continues, the North Magnetic Pole could soon be in Russia, a development that would have required updating the world magnetic model yet again. But here's where we need to be careful. Not all amateur research is rigorous or accurate. The internet is full of sensationalized claims about imminent pole shifts, catastrophic reversals, and apocalyptic consequences. Separating signal from noise requires critical thinking and scientific literacy. The legitimate amateur, researchers, people like Stuart Green and members of the Intermagnet Network, follow scientific methods, publish their data openly, and welcome peer review. They're contributing valuable observations to our understanding of Earth's magnetic field. The sensationalists make dramatic predictions without evidence, cherry-pick data to support predetermined conclusions, and often mix legitimate science with pseudoscience, conspiracy theories, and apocalyptic thinking. The challenge for the public and for scientists is distinguishing between these groups. Both use similar language. Both talk about magnetic reversals, solar storms, and potential catastrophes. But only one is contributing to actual scientific understanding. Dr. Kieran Beggan of the British Geological Survey has been working to bridge the gap between amateur enthusiasts and professional researchers. Valuable data is being collected by amateurs, he said in a 2020 interview, but it needs to be properly calibrated, contextualized, and analyzed using rigorous methods. That's where professional scientists can help. What's clear is that interest in Earth's magnetic field is growing, both in the scientific community and among the public. The question of when the next reversal will occur has gone from an obscure academic topic to something that thousands of people worldwide are actively discussing and researching, and that growing awareness is raising uncomfortable questions. If we know a reversal is inevitable, if we know it could potentially happen in our lifetimes, or our children's lifetimes, and if we know the consequences could be catastrophic for modern civilization, what should we be doing differently? Should governments be investing more in magnetic field research and monitoring? Should we be hardening our infrastructure more aggressively? Should space agencies be developing contingency plans for operating satellite networks during a period of weak magnetic protection? And perhaps most uncomfortably, should we be telling the public more clearly about the risks, or would that create unnecessary panic about a slow-moving threat we can't prevent? These are the questions that keep scientists, policymakers, and yes, amateur researchers awake at night. And they're questions we need to answer soon, because while reversals unfold over thousands of years, the decisions we make today will determine whether civilization survives the next one. Section 10. Mars, the dead planet. If you want to understand what happens to a planet without magnetic protection, look up at Mars on a clear night. That dim red dot in the sky is a warning from our cosmic neighbour, a cautionary tale written across 4 billion years of planetary death. Mars wasn't always dead. The evidence is overwhelming. Ancient river valleys carved into its surface, dried lake beds, minerals that only form in the presence of water, and even what might be an ancient ocean basin covering much of the northern hemisphere. Between 4 billion and 3.5 billion years ago, Mars had liquid water on its surface, a thick atmosphere, and possibly conditions suitable for life. Then something catastrophic happened. Mars died. The culprit was the same force protecting Earth right now, the magnetic field, or rather, the loss of it. Data from NASA's MAVEN spacecraft, Mars Atmosphere and Volatile Evolution mission, which has been orbiting Mars since 2014, has revealed exactly what happened, and it's terrifying. Mars once had a global magnetic field, generated by a dynamo in its molten core just like Earth. But Mars is smaller than Earth, about half the diameter and 1/10 the mass. Smaller planets cool faster. Somewhere between 4 billion and 3.8 billion years ago, Mars's core cooled enough that the dynamo shut down. The magnetic field collapsed. Without magnetic protection, the solar wind began stripping away Mars's atmosphere directly. NASA estimates that Mars is currently losing about 100 grams of atmosphere per second to space, roughly the weight of a hamburger every second. That might not sound like much, but over billions of years it adds up. Today, Mars's atmospheric pressure at the surface is less than 1% of Earth's. The air is so thin that liquid water cannot exist on the surface, it immediately evaporates or freezes. Any life that might have evolved during Mars's wet period would have been extinguished as the planet dried out and froze. The MAVEN data have revealed something even more disturbing. The rate of atmospheric loss accelerates during solar storms. When a major coronal mass ejection hits Mars, the atmospheric escape rate can increase by a factor of 10 or more. Without a magnetic shield, the enhanced solar wind tears through the thin atmosphere like a gale through gossamer. Dr. Bruce Jakosky, MAVEN's principal investigator, stated in a 2017 press conference, "Mars lost its magnetic field and as a result lost most of its atmosphere to space. We're watching that process continue today. It's a slow catastrophe unfolding over billions of years." But here's the critical question. Could this happen to Earth? The answer is nuanced. Earth is larger than Mars, which means our core cools more slowly. Current estimates suggest Earth's core will remain molten for at least another few billion years, long enough that the Sun's evolution into a red giant will destroy Earth first. So we don't need to worry about Earth becoming Mars on a billion-year timescale. But what about shorter timescales? What happens during a magnetic reversal, when Earth's field weakens to 10–20% of normal for thousands of years? During a reversal, we won't lose our magnetic field entirely. It will just be weak and chaotic. That's very different from Mars's situation, where the field disappeared completely. But even a weak, unstable field could allow significantly more atmospheric stripping than occurs currently. NASA scientists have modelled what would happen to Earth's atmosphere during a magnetic reversal. The results are sobering but not apocalyptic. Over the course of a 5,000-year reversal, Earth might lose a few percent of its upper atmosphere, primarily lighter gases like hydrogen and helium escaping from the thermosphere and exosphere, the outermost layers of our atmosphere. This wouldn't be enough to threaten life or make Earth uninhabitable. The bulk of our atmosphere, the nitrogen and oxygen we breathe, would remain intact, but there would be measurable loss, and if reversals happen frequently over geological time, the cumulative effect could be significant. Some scientists have speculated that Earth's history of frequent magnetic reversals might have actually influenced the evolution of our atmosphere, preventing it from becoming as thick as Venus's atmosphere, or allowing more hydrogen to escape, which kept Earth from developing a runaway greenhouse effect. But here's where Mars teaches us a darker lesson. It's not just about the magnetic field. It's about the cascade of failures that can occur when planetary protective systems break down. Mars lost its magnetic field. That allowed atmospheric stripping. The loss of atmosphere reduced surface pressure and temperature. Liquid water became impossible. The carbon cycle, which regulates planetary temperature, broke down. The planet froze and dried out. Any life that existed disappeared. Earth is protected by multiple systems: our magnetic field, our thick atmosphere, our oceans, and our active geology. These systems interact and support each other. The magnetic field protects the atmosphere. The atmosphere protects the surface. The oceans regulate temperature. Active geology recycles carbon and maintains the conditions for life. But these systems aren't independent, they're coupled. Weaken one, and the others can be affected. During a magnetic reversal, we're essentially conducting a natural experiment on one of Earth's critical protective systems, and we don't know all the potential consequences. Venus offers another cautionary tale. Venus is nearly Earth's twin in size and mass, but it has no magnetic field, or at most, a very weak one induced by the interaction of the solar wind with its atmosphere. Venus's surface temperature is hot enough to melt lead, and its atmospheric pressure is 90 times Earth's. Did Venus once have a magnetic field? Did it lose it? Did that loss contribute to the runaway greenhouse effect that turned Venus into hell? These are open questions in planetary science, but they highlight how complex planetary habitability is. Earth occupies a Goldilocks zone, not just in terms of distance from the Sun, but in terms of having the right combination of magnetic protection, atmospheric composition, temperature, and geological activity. Change any one of these factors significantly, and we could slide toward a Mars-like frozen desert or a Venus-like toxic hothouse. The magnetic field is one piece of that delicate balance, and right now that piece is changing in ways we don't fully understand, at rates that appear to be accelerating, with potential consequences that range from minor inconveniences to civilization-threatening catastrophes. Which brings us to perhaps the most important question of all: is there anything we can actually do about it? Can we influence Earth's magnetic field? Can we protect ourselves artificially if the natural shield fails? Or are we completely at the mercy of processes happening 1,800 miles beneath our feet, driven by a molten iron ocean we can never reach, never directly study, and never control? The answers might surprise you. Section 11. Can we protect ourselves? Imagine trying to shield an entire planet from a cosmic storm. Not a small area, not a city or a country, but every square mile of Earth's surface from pole to pole. It sounds impossible. But scientists have actually considered whether artificial magnetic shields could protect us if Earth's natural field fails. The idea isn't as far-fetched as it might seem. In 2017, NASA researchers published a study proposing an artificial magnetic shield for Mars, a giant magnetic dipole positioned at the Mars-Sun Lagrange point, L1, about 200,000 miles from Mars. This artificial field would deflect the solar wind around Mars, potentially allowing the planet's atmosphere to naturally rebuild over decades or centuries. The proposal was serious enough that NASA's Planetary Science Division funded initial feasibility studies. The technology would require creating a magnetic field about 10,000 times stronger than Earth's field, but over a much smaller area. The power requirements would be enormous, megawatts of continuous power, but potentially achievable with advanced nuclear reactors or solar arrays. If we can theoretically shield Mars, could we shield Earth? Dr. Jim Green, then NASA's chief scientist, addressed this question in a 2017 presentation. Creating an artificial magnetosphere for Mars is an enormous engineering challenge, but it's within the realm of possibility with advanced technology. For Earth, the challenge would be orders of magnitude greater, because Earth is larger and requires a much stronger field. But here's the critical point. We wouldn't need to replace Earth's entire magnetic field during a reversal. The field would still exist. It would just be weak and chaotic. What we'd need to do is supplement the natural field, creating enhanced protection in critical regions. Several proposals have been floated: orbital magnetic generators, a constellation of satellites equipped with powerful electromagnets positioned in key orbits to deflect solar wind particles away from Earth. This would require hundreds or thousands of satellites, massive power generation, and unprecedented international cooperation. Ground-based field enhancement, large-scale electromagnetic installations at strategic locations on Earth's surface, creating localized field enhancements that could protect populated areas or critical infrastructure. Think of them as magnetic umbrellas for cities. Upper atmosphere ionization. Using powerful radio transmitters to artificially ionize regions of the upper atmosphere, creating conductive layers that could help deflect charged particles. This is similar to existing technology like HAARP, High Frequency Active Auroral Research Program, but on a much larger scale. All of these proposals face enormous technical, financial, and political challenges. But they're not impossible. With sufficient motivation and resources, humanity could potentially create artificial magnetic protection. But There's a simpler, more immediate approach: hardening our infrastructure and developing better early warning systems. Power grids can be protected with devices called GIC, geomagnetically induced current, blockers, which prevent damaging currents from flowing through transformers during geomagnetic storms. These devices cost about $40,000 per transformer. Expensive, but far cheaper than replacing damaged transformers that can cost millions each. The problem is implementation. A 2019 study by the US National Academy of Sciences found that protecting just the critical nodes in the US power grid would require installing GIC blockers on approximately 1,000 transformers at a total cost of around $40 million. That's a tiny fraction of the potential economic damage from a major geomagnetic storm. But utilities have been slow to invest. Why? Partly because geomagnetic storms are rare. A utility company might go decades without experiencing a major event, making it hard to justify the upfront investment. And partly because responsibility is unclear. Should utilities bear the cost? Or should it be government funded as a national security issue? Satellite protection is more straightforward. Modern satellites are already built with radiation shielding and fault-tolerant electronics. As the South Atlantic anomaly expands, satellite manufacturers are simply adding more shielding and designing orbital paths that minimize time spent in high radiation zones. But here's the limitation. Shielding adds weight, and weight is the enemy in space launch. Every pound of shielding is a pound that could have been scientific instruments or additional fuel. There's a trade-off between protection and capability. For human space exploration, the challenges are even more severe. Astronauts on the International Space Station are protected by Earth's magnetosphere, even though they're in orbit. But astronauts travelling to the Moon or Mars would spend weeks or months outside magnetic protection, exposed to the full force of cosmic radiation and solar storms. NASA's Artemis program, which plans to return humans to the Moon in the 2020s, includes advanced radiation monitoring and shelter systems. The proposed Gateway station, which will orbit the Moon, will have a dedicated radiation shelter where astronauts can retreat during solar storms. But what if a major solar storm hits while astronauts are on the lunar surface, far from the Gateway? They'd have to rely on surface habitats with radiation shielding, possibly using lunar soil piled on top of structures as a cheap, effective shield. For Mars missions, the challenge is even greater. The journey to Mars takes 6 to 9 months, during which astronauts would be exposed to deep space radiation. Plans for Mars missions include water-lined walls in spacecraft, water is an excellent radiation shield, and possibly pharmaceutical countermeasures, drugs that could reduce radiation damage at the cellular level. But all of these approaches assume something important. They assume we have a warning. If we can detect a solar storm before it hits, we can take protective action, shut down transformers, put satellites in safe mode, shelter astronauts, divert aircraft from high radiation flight paths. And that's where space weather forecasting becomes critical. NOAA's Space Weather Prediction Center operates 24/7, monitoring the sun for signs of eruptions that could send coronal mass ejections toward Earth. When they detect a major solar flare on the side of the sun facing Earth, they can issue warnings with lead times of 15 minutes to several hours, depending on the event. Satellites like NASA's Duskov Deep Space Climate Observatory are positioned at the L1 Lagrange point, about 1 million miles from Earth toward the Sun. When a coronal mass ejection passes DiscoVR, we get about 15 to 60 minutes of warning before it hits Earth, enough time to activate emergency procedures. But current forecasting is far from perfect. We can see when the Sun erupts, but predicting exactly where the ejection will go and how strong it will be when it arrives is difficult. It's like trying to predict where a hurricane will make landfall days in advance. We can give probabilities and general warnings, but precision is elusive. Improving space weather forecasting is a priority for NASA, NOAA, ESA, and other space agencies. New satellite missions are planned, including improved solar monitoring from multiple vantage points to give us a 360-degree view of the Sun. Advanced computer models are being developed to better predict how solar storms propagate through space and interact with Earth's magnetosphere, But here's the uncomfortable truth. All of these measures, hardened infrastructure, protected satellites, space weather forecasting, are designed for our current situation with a relatively strong magnetic field providing baseline protection. If Earth's magnetic field weakens to 10–20% of its current strength during a reversal, everything changes. Solar storms that are currently manageable become catastrophic. Cosmic radiation levels that are currently acceptable become dangerous. The South Atlantic anomaly could expand to cover half the planet or more. Could civilization survive a magnetic reversal? Almost certainly yes. Humans lived through the Brunhes-Matuyama reversal 7,000 to 80,000 years ago, and the Lasham excursion 42,000 years ago. But could technological civilization survive intact, with satellites, power grids, and electronic infrastructure functioning? That's a much harder question. The honest answer is, nobody knows. We've never faced this challenge before. And with the magnetic field currently weakening, with the South Atlantic anomaly expanding, and with the magnetic poles racing across the planet at unprecedented speeds, we might find out sooner than we'd like. Section 12. The timeline. When will it happen? This is the question everyone wants answered. When will the next magnetic reversal occur? Are we talking about next year, next century, or next millennium? Scientists hate this question because the honest answer is, we don't know. But we can look at the evidence and make educated assessments about what's happening and what might happen over different timescales. Short term, next 10 to 50 years. A full magnetic reversal beginning in the next few decades is extremely unlikely, essentially impossible according to mainstream geophysical understanding. Reversals unfold over centuries to millennia, not years to decades. What is possible, and what's already happening, is continued weakening of the field, expansion of the South Atlantic anomaly, and continued rapid movement of the magnetic poles. Dr. Julian Aubert's computer model suggests that if current trends continue, the South Atlantic anomaly could expand to cover much of the southern hemisphere within 50–100 years. This would significantly increase radiation exposure for satellites in low Earth orbit and could make certain orbital configurations untenable. The magnetic North Pole will likely continue its race towards Siberia, possibly crossing into Russian territory within the next decade. This will require frequent updates to the world magnetic model and could affect navigation systems that rely on magnetic heading. But a full reversal starting in the next few decades. The geophysical evidence doesn't support that timeline. Medium term, next 100–1,000 years. This is where things get more uncertain and more concerning. If Earth's magnetic field is in the early stages of a reversal, which some scientists believe based on the reverse flux patches in the core and the current weakening trends, then the reversal process could accelerate over the next few centuries. Geological studies of past reversals show that the weakening phase can take several centuries to several millennia. We've been in a weakening phase for at least the past 2,000 years, based on archaeological magnetic measurements from pottery and ancient structures. If this trend continues or accelerates, we could see field strength drop to 50% of current levels within a few centuries. At that point, the effects would be impossible to ignore. Auroras would regularly appear at mid-latitudes. Satellite operations would become significantly more challenging. Radiation exposure at high altitudes, affecting air travel, would increase measurably. And we'd likely be committed to a full reversal process that would unfold over the following millennia. Dr. Brad Singer's high-precision dating of past reversals suggests that once a reversal begins in earnest, the fastest phase, when the field actually flips polarity, can occur in less than 100 years. That's geologically rapid, but still multiple human generations. Long-term, next 1,000,000 to 100,000 years. On timescales of millennia, a magnetic reversal is not just likely, it's essentially guaranteed. The geological record is unambiguous. Reversals happen, they're a normal part of Earth's magnetic field behaviour, and we're currently in an unusually long period of stable polarity. Statistical analysis of reversal frequency over the past 20 million years suggests that the probability of a reversal beginning in any given millennium is roughly 1 to 5%, depending on how you calculate it. Over 10,000 years, the cumulative probability approaches certainty. But here's the critical insight. Even if a reversal doesn't occur, the magnetic field will continue to fluctuate, weaken in some regions, strengthen in others, and generally behave in ways that we need to monitor and adapt to. The South Atlantic anomaly might expand or it might contract. Core dynamics are complex and can reverse trends unpredictably. The magnetic poles will continue to wander, possibly describing wide loops across Earth's surface. Field strength will vary regionally and over time. In other words, the magnetic field is not a static shield. It's a dynamic, evolving structure responding to processes in the deep interior that we can only dimly perceive. What about catastrophic scenarios? Some researchers have suggested that magnetic reversals could potentially occur much faster than the consensus view suggests, possibly in decades rather than millennia. This is based on alternative interpretations of the geological record and speculative models of core dynamics. The most cited evidence for rapid reversals comes from a 1995 study of volcanic rocks in Oregon that appeared to show magnetic field directions changing by several degrees per day, implying a reversal could occur in weeks or months. However, subsequent research has cast serious doubt on this interpretation. The rapid changes were likely caused by local geological effects rather than global magnetic field reversals. The scientific consensus remains that reversals take centuries to millennia at a minimum. Dr. Catherine Constable, a geomagnetism expert at Scripps Institution of Oceanography, addressed the rapid reversal claims in a 2018 review. While the exact duration of past reversals remains uncertain due to dating limitations, there is no credible evidence for reversal timescales shorter than centuries. Claims of weeks or months are not supported by the broader geological record, so we can rule out apocalyptic scenarios of the magnetic field flipping overnight. But we can't rule out faster than expected weakening, expansion of anomalies like the South Atlantic anomaly, and potential for a reversal to begin within the next few centuries. What triggers a reversal? This is the $64,000 question in geophysics. If we understood what triggers reversals, we could potentially predict when the next one will occur. But the core is a chaotic system. Small changes can cascade into major transitions, and the exact configuration that tips the system from stable polarity to reversal is still debated. Current theories suggest that reversals occur when reversed flux patches in the outer core grow large enough and strong enough to overwhelm the main field. The African and Siberian reversed flux patches are currently growing, which is why some scientists think we might be in the early stages of a reversal. But early stages in geophysical terms mean centuries to millennia, not something that will happen in any living person's lifetime. Or will it? Here's the uncomfortable truth. The core is 1/800 miles beneath our feet. We've never sampled it directly. Everything we know comes from indirect measurements and computer models that are only as good as our understanding of the physics involved. There could be processes occurring in the core that we don't understand, that don't appear in our models, that could accelerate changes in ways we can't predict. Probably not. Almost certainly not. But not definitely not. And that uncertainty, that small but non-zero possibility that we could be surprised by how fast things change, is what keeps scientists monitoring Earth's magnetic field with increasing urgency. Which brings us to the final question. What does all of this mean for you, personally, for your children, for humanity's future? Section 13. What it means for humanity. Let's bring this back to Earth, literally. You're sitting somewhere right now watching this video, living your life under the invisible protection of a magnetic shield that has been operating continuously for over 3 billion years. What does this story mean for your actual day-to-day existence? In the short term, the next few decades, probably not much. You'll likely experience a few minor effects. GPS systems might occasionally be less accurate as the magnetic poles continue their rapid movement, and as the world magnetic model struggles to keep up. You might see auroras at lower latitudes than historically typical, and honestly, that would be spectacular, not scary. If you fly frequently at high altitudes, your cumulative radiation exposure might be slightly higher, but still well within safe limits. Power grid operators and satellite companies will face increasing challenges. Some satellites might fail more frequently in the South Atlantic anomaly. Some orbital configurations might become impractical, but these are problems that engineers and scientists are already working to solve. If you live in the Southern Hemisphere, particularly in South America or Southern Africa, you might notice more frequent disruptions to GPS and communications as the South Atlantic anomaly expands over your region. But these will likely be intermittent annoyances, not catastrophic failures. In other words, for the average person alive today, Earth's magnetic field changes are a fascinating scientific story, but not an immediate personal threat. But zoom out, think longer term, think generationally. Your children or grandchildren might live in a world where auroras are common at mid-latitudes, where certain satellite orbits are avoided due to high radiation. Power grids need to be shut down preemptively several times per year during geomagnetic storms. High-altitude air travel requires higher standards for radiation monitoring. These would be manageable challenges for an advanced technological civilization. Inconvenient, yes. Expensive, certainly. But not civilization ending. Now think even longer term. If Earth's magnetic field continues weakening, if we're truly in the early stages of a reversal, then centuries from now, humanity might face genuine challenges. Maintaining satellite infrastructure during a period of greatly weakened magnetic protection might require entirely new approaches, perhaps moving critical satellites to higher orbits beyond the most intense radiation belts, or creating orbital magnetic shields as discussed earlier. Power grids might need fundamental redesigns to handle frequent and severe geomagnetic storms. This could actually drive innovation in energy systems, pushing us toward more distributed, resilient grid architectures with local generation and storage. Space exploration would become more challenging. Getting to Mars during a period of a weakened Earth magnetic field would mean launching astronauts into an even more hostile radiation environment than they already face. Mission planners would need to account for this with better shielding, faster transit times, or pharmaceutical countermeasures. Agriculture and ecosystems could be affected if cosmic radiation increases significantly during a reversal. Higher mutation rates in crops and wildlife could have unpredictable effects. Some species might be more vulnerable than others, but here's the critical point. Humanity has survived magnetic reversals before. Homo erectus lived through the Brunhes-Matuyama reversal 780,000 years ago. Modern humans lived through the Lachamp excursion 42,000 years ago. We're still here. The difference is that those early humans had Stone Age technology. They didn't rely on satellites, power grids, or electronic infrastructure. They couldn't lose capabilities that they'd never developed. We can. That's the existential question. Can technological civilization maintain itself through a magnetic reversal? Can we keep satellites in orbit, power grids running, and electronic systems functioning during a period of weakened magnetic protection, lasting thousands of years? Nobody knows the answer, because we've never tried. We've only had advanced technology for about 100 years, the blink of an eye in geological terms. The next magnetic reversal will be humanity's first test of whether our technological civilization is robust enough to survive long-term planetary changes. But here's the optimistic perspective. Knowledge is power. Our ancestors who lived through past reversals didn't know what was happening. They couldn't measure the magnetic field, couldn't predict solar storms, couldn't understand the connection between the sun, the magnetosphere, and the effects they were witnessing. We can. We have satellites monitoring the sun 24/7, ready to give us hours or even days of warning before a major solar storm hits. We have the ability to temporarily shut down vulnerable infrastructure to protect it. We understand the physics of magnetic field generation and reversal, even if we can't predict exact timings. We can develop new technologies, better radiation shielding, artificial magnetic protection, hardened electronics. Most importantly, we're aware of the challenge. That awareness by itself is valuable. It allows us to prepare, to adapt, to engineer solutions. Dr. Daniel Baker, whose research we've discussed throughout this investigation, put it this way in a 2019 interview. Magnetic reversals are inevitable. Major solar storms are inevitable. These are facts of living on an active planet orbiting an active star. But we're not helpless. We're a technological species capable of understanding these threats and developing countermeasures. The question isn't whether we can survive the next reversal. The question is whether we'll have the foresight and will to prepare. And that's really what this entire story comes down to. Foresight and will. We know the threat exists. We know it's inevitable on long timescales and possible on shorter timescales. We know the consequences could range from inconvenient to catastrophic, depending on how we prepare. What we do with that knowledge, whether we invest in monitoring, research and protective infrastructure, or whether we ignore a slow-moving threat in favour of immediate concerns, will determine whether future generations look back at us as the ancestors who prepared wisely, or the ancestors who ignored warning signs. Because make no mistake, this is one of those rare situations where we have a warning of a potential civilization-scale challenge. We can see it coming, even if we can't predict the exact timing. That puts us in a uniquely fortunate position compared to threats like asteroid impacts or supervolcano eruptions, which can occur with little or no warning. So what should we be doing? What's the path forward?